Hi there, everyone. My name's Meg Hennessy, and I'm a teacher here in Houston, Texas. I've been teaching the IB for 15 years, maybe, and I'm looking forward to talking to you about proton transfer reactions. I have a QR code on this slide that shows you where I put the notes. There's both a filled version and a unfilled version, whatever you prefer. And I also threw that link in chat, and I'll try to make sure to keep putting it there. Just to make sure y'all can hear me, can someone just throw something in the chat that says hello or thank you for the thumbs up? I appreciate you. Okay, welcome everyone. R 3.1 is a pretty big unit, all about proton transfer reactions. And we used to call it acid-base chemistry. It's the same thing. On the left-hand side of this slide, I have the acyl stuff. And on the right-hand side, I have what we're going to be focusing on today, which is mostly the HL stuff. I changed the order around a little bit. I decided to talk about buffers before we talk about titration curves and indicators, because indicators are just buffer systems. So it made more sense to me. The order here is just the order in the actual IB syllabus. Okay, let's go. And so I start with the easy question, and that is, what is the pH of neutral water at room temperature? And I hope you're all thinking, wow, this is too easy. The answer is just 7. And I claim this is just something maybe you know. But maybe I can make this question a little bit more rigorous instead of you just typing in the 7s, which I totally appreciate. What if I said I want to change the temperature to 340 Kelvin? At that point, the kW has taken on a different value. So I looked it up in a table. It's no longer in our data booklet. It would be given in a problem. And I have some sample questions coming up in a second. But what if we were told that the pKW was 13.5? What would the pH of neutral water be? And some of you are writing it down, but just to slow this down for a second, I want to remind you what the kW is. The kW is the equilibrium constant for the autoionization of water. So that means that 2 water molecules come together and one donates a proton to the other. And so this guy who gained the proton is going to be a base. This guy who lost the proton is going to be an acid. And on the other side, you must recognize the conjugate acid and the conjugate base. The K here is going to be the concentration of the products multiplied together over the concentration of the reactants raised to their powers. Because water is a liquid, it doesn't appear in the equilibrium constant expression. Now, I gave you the pKW, and just as a refresher, the prefix P means take minus the log of. So I told you minus the log of the kW is 13.5. That means kW is 10 to the minus 13.5. One more thing we have to notice is that the concentrations are equal because we have pure water. And so that means that the concentrations of hydronium and hydroxide are equal to each other if the only ingredient we added was water. So we could write that Kw is equal to hydronium squared. And we can solve that, and you can be a little bit cheeky and remember some exponent rules, or you can 100% use your calculator. But I wanted the pH of this solution. The pH is going to be minus the log of the concentration of hydronium. And so I'm going to get 6.75. And a few of you wrote that. A few of you already knew that if you took this pKW and you divided it by 1/2, you would get the pH of a neutral solution. So I wanted to remind you that a neutral solution doesn't necessarily have a pH of 7. A neutral solution simply has the concentrations of hydronium and hydroxide being equal to each other. So as the temperature goes up, you're going to notice that the pH does go down, but we still have pure water, and that's described as neutral. So I've put the QR code on some of the slides to help you get to the notes. I've also dumped the link into the chat. I hope everyone can see it. And I'm going to give you a practice problem in just a second. There you go. There are 3 quick multiple choice questions for you to check your understanding of KW. I'm going to give you about a minute and a half, and I'll answer any questions I can in the chat. Okay, I just opened up the Q&A in case you couldn't see it, or in case I just had it closed and I couldn't see it. You can put questions there or in the chat. I'll do my best to keep answering them. I gave you these 3 quick multiple choice questions just to make sure we're all on the same page with KW. Decidedly hit the wrong button on my computer, but that's totally normal. Here we see that as the temperature is increasing from 298 Kelvin to 310 Kelvin, the K has increased from 1 times 10 to the minus 14th to 2.4 times 10 to the minus 14th. It has become larger. If the K increases as temperature increases, that means that heat is a reactant. Le Chatelier tells me as the amount of heat or temperature goes up, this reaction will shift to the right, making more products, making K a larger number. Temperature is the only thing that changes the value of K. Okie dokie. Choice A says the pH of pure water decreases when heated. That's true. We actually just saw that in the last problem. As K becomes larger, that means we're going to be making more hydronium. When we make more hydronium, the pH is going to go down. It's a more acidic solution, if you will. There's more H3O plus present. The enthalpy of ionization is endothermic, so that's incorrect. The concentration of hydroxide is in fact higher, and the conductivity, because the concentration of those ions is higher, will be greater. So A is my best answer to that. Got another request for the slide. So I hope this is working. Is everyone able to see in the folder that there are 2 things, the slides both filled and unfilled? Next up, we're given the pKw at another temperature. It's 14.52. What's the pH of pure water? Aisha taught me that I could just multiply this by 1/2. And finally, if the temperature goes down, we know that K is going to decrease. As K decreases, less hydronium will be formed. So the pH will go up. Finally, because we only have water, the concentration of hydronium and hydroxide will be equal. So the best choice is A. Thank you, Marty. I appreciate it. Everything else I do today, I'm going to do at 298 Kelvin. I just wanted to practice the KW thing for a minute and see how temperature affected it to give you some background on what we're doing. I'd like to take that pure water and I'd like to add a strong base to it. The first thing we're supposed to learn about in the HL section is the pOH scale. So I'm going to take 0.04 grams of sodium hydroxide. I'm going to add it to 75 cubic centimeters of water, and I'd like to calculate the pH, the pOH, on and on. Oh my goodness. 0.04 grams of sodium hydroxide. I could convert it to moles by dividing by the molar mass. I would get 0.001 moles of sodium hydroxide. Sodium hydroxide is a strong base, so it dissociates completely. And so this is the same as having 0.001 moles of hydroxide. If I wanted to know the concentration of hydroxide, I would take the number of moles and divide it by the number of decimeters cubed. I get 0.0133 moles per decimeter cubed. The POH, pardon me, is minus the log of the concentration of hydroxide. So I plop that in my calculator and I get 1.88. Now you saw a second ago that Kw was equal to the concentration of hydronium times the concentration of hydroxide. If I wanted to use some math skills, I could take minus the log of both sides, and that means minus the log of the Kw would be equal to minus the log of this product. But when I take the log of the product, I can separate it into their sum. And so I could tell you that 14 is equal to the sum of the pH and the POH. I imagine many of you know this relationship and this relationship, and so this should allow us to finish the problem. The pH is going to be 14 minus 1.88. And the concentration of hydronium is going to be 1 times 10 to the minus 14th divided by 0.0133. Put a label on this so you don't judge me too bad. And I think I did all the things. I think that we found the concentration of hydroxide. I think we found the POH by taking minus the log of it. I think we said that the sum of the POH and the pH is 14, so we could figure out the pH is 12.12. And then for the concentration of hydronium, we could take 10 to the minus 12.12, or we could take Kw divided by hydroxide. In either case, we would get this value. So again, just a brief introduction into hydroxide and the POH, and a practice set of questions for you about how we handled some strong base solutions. So again, I'll answer a couple questions in the chat and give you just a minute to read through these. All right, hopefully you got a chance to read them. In the first problem, we have 10 cubic centimeters of sodium hydroxide, and we're going to dilute it with a whole bunch of water so that at the end we'll have 1,000 cubic centimeters of solution. So this solution is changing its volume from 10 to 1,000 or by 2 orders of magnitude. Because pH is a log scale, that seems like a really useful thing to know. Now, I know this is a basic solution, so I expect the pH to be higher than 7. So options C and D are both going to be wrong. The initial pH is going to be maybe not too hard to figure out. The POH is going to be minus the log of the concentration of hydroxide, so minus the log of 0.01, which is 2. So the initial pH would be 14 minus that is 12. And if I dilute the solution by 2 orders of magnitude, my expectation is that the pH will be 10. Same game again. I'm going to lime a lake to mitigate some acid rain. The pH of the lake water rose from 4.5 to 6.5. What is the change in concentration of hydroxide ions? So this solution is becoming more basic because the pH is going up. So the concentration of hydroxide ion must be going up. So again, answers C and D seem incorrect. Because pH is a log scale, B is the best answer. We're changing by 2 orders of magnitude because the pH is changing by 2 units. Last but not least, a solution of methylpropanoic acid has a known concentration of H+. What's its concentration of hydroxide? We don't have to worry about the details of a weak acid problem here. We're given the information we need, which is that H+ is a known 0.00205. We know that the concentration of hydroxide then should be Kw, or 1 times 10 to the minus 14th, divided by that concentration. And so we can write down an answer. So again, all of these questions are super similar to IB questions, and I hope that they are building some confidence that if you're asked some pH, POH style questions with the autoionization of water, that you're gonna do a great job. Bethany asked me what I mean by I diluted by 2 orders of magnitude. So I meant that the volume of this solution went from 10 to 1,000. And so that's 2 orders of magnitude, 10 to 100, and then 100 to 1,000. If I did that in more steps to be more clear, I could use the dilution formula that says C1V1 equals C2V2. The initial concentration is 0.01 moles per decimeter cubed. The initial volume is 10 cubic centimeters. The final concentration is what I'm trying to solve for. The final volume is 1,000 cubic centimeters. And so here, I hope you also maybe see that I diluted this from 1 times 10 to the minus 10 to 1 times 10 to the minus, Jesus. I diluted this from 1 times 10 to the minus 2, pardon me, to 1 times 10 to the minus 4, or 2 orders of magnitude. I hope that clarified a little bit, Bethany. Okay. So here is a weak acid problem. I'm going to take ethanoic acid, and I made a 0.4 molar solution of it, and I'd like to know the pH, and the information that's given to me in the problem is the pKa. And to solve these problems, I recommend just going back to your understanding of equilibrium, which was back in R2.3, and trying to write down the equation that we're studying. So we're showing that ethanoic acid is a weak acid. We know that because the pKa is given to us. So I'm going to draw that with equilibrium arrows representing the fact that it partially dissociates. And when an acid dissociates, what that means is it gives its proton to water, making a conjugate base and hydronium ions. So that's the reaction that I'm studying. And initially, I have 0.4 molar. Everything I put in this table is going to be in moles per decimeter cubed, so I'm not going to include any units. Not that I've been doing a great job with it anyway. The change that's going to occur as this system comes to equilibrium is that some of the acid is going to hydrolyze, but not very much. And when the acid hydrolyzes, it's going to make conjugate base and hydronium. Now, some of you are wondering why I'm omitting the water column. It's because water is still a liquid as opposed to an aqueous species, so it doesn't appear in an equilibrium constant expression. Its concentration doesn't change. So I'm just ignoring it. At equilibrium, I'm going to take the initial amount of ethanoic acid, and I'm going to see how it changed. So I started with 0.4, but it went down a little bit. I started with 0 of the ethanoate ion, and it went up a little bit. I started with 0 of the hydronium ion, and it went up a little bit. So I have figured out the equilibrium concentrations of all of the species, but I also know how to write the equilibrium constant expression. It's going to be equal to the concentration of the base, that's the first product, which was X, times the concentration of hydronium, that's also X, divided by the concentration of the acid, ethanoic acid. It's also equal to 10 to the minus 4.76. Now, we make an approximation in IB chemistry, And that approximation is that because this only partially dissociates and because it is a quite weak acid, the amount that dissociates compared to the initial amount of the acid is negligible. So we make the approximation that the initial amount is about the same as the amount we find at equilibrium. There we go. And when we make that approximation, we avoid having to solve a quadratic. And we avoid that at all times. Okay, trying to solve this, I'm going to say that x squared is equal to 10 to the minus 4.76 times 0.4. And it's just hard for me to use a calculator and write and talk to you all at the same time. Let me look at my notes. I took the square root of both sides to find that x is equal to 2.64 times 10 to the minus 3. And the pH, which is going to be minus the log of x, is 2.58. So we have done a weak acid calculation. We figured out what the pH of a weak acid solution might be. I got 2 questions about this, so just to take a break and answer those. The first question is, how did I know to use a rice table? It's because I knew this was a weak acid. I knew this was a weak acid because the pKa was given to me. I also know the strong acids in IB chemistry are HCl, HBr, HNO3, H2SO4. I'm missing the 5th one, guys. You want to help me out? It's not perchloric. Oh my gosh. I'm now trying to cheat. HI is what people are telling me. It's not phosphoric, but I appreciate that. Thank you for the save on HI. IB chemistry didn't have 5 before this new curriculum rewrite, but there are 5 now, and I very much appreciate the chat. So I used rice for 2 reasons. 1, because I was given a Ka, so I knew I was setting up an equilibrium, and 2, because it wasn't one of the 5 strong acids that with a little bit of help, I got people writing hi to me. I didn't get it. I was like, hi to you too. The second question I got was, why did I assume that X was negligible compared to 0.4? And I like to think about it in terms of money because I think it's something that many of us understand. I live in the US, and so Elon Musk is a public figure here. And I like to talk about what happens if I were to find a $100 bill on the ground. A $100 bill would more than take my family out for dinner. It would be a great night and a special treat for a Wednesday. It would not maybe change my life, but it would certainly change my week. On the other hand, if Elon Musk were to find a $100 bill, it wouldn't change his life. He has billions of dollars. So when we compare how much that $100 is to someone who has a lot, it is negligible. But when we compare that $100 to someone who has none, it is not negligible. It would be an important change to my week. So I think about the difference between the acid only dissociating a little bit, its concentration is barely changed. But when we think about how much hydronium we make in that solution, we make quite a bit because there's so little to start with. So I'm just saying that the amount of acid that hydrolyzes doesn't change the amount of acid that's in the solution. I hope that helped, Evelyn. The reason that we did x times x is because the equilibrium constant expression has the concentration of both products. So one x is the concentration of the base, and the other x is the concentration of the hydronium ion. And in the bottom, I have the 0.4 minus x. So I was just filling in the equilibrium constant expression. Hope that clarifies how we did it. We have solved our first weak acid problem. We got a pH of 2.58. Now you can think, how would you know that this is a weak acid? Well, if this were one of the big 5, we know that the pH would just be equal to minus the log of the concentration. So let me do that super fast on a calculator. and I get 0.4. So if this had been a strong acid, the pH would have been 0.4. This is not a strong acid, so the pH is quite a bit higher. It is 2.58. Here's one for you to practice. I gave you the Ka of a weak acid and its concentration. I'm curious, what is the pH of that solution? It, I hope this question looks really similar. You can set up the rice table. You would then solve for x and take minus the log of x to find the pH. So 2-methylpropanoic acid. If I have to write this out, I guess 2-methyl. Oof. Is that beast of a compound? So I would write something like this plus water makes this plus hydronium. I would start with the initial concentrations, the change, the equilibrium values. But many of you who have practiced this problem a lot might recognize that it's always exactly the same setup. And so you might have skipped directly to the equation I just wrote down, where we say Ka is equal to x squared over 0.020. And once again, I would make the approximation that the amount of acid that hydrolyzed is negligible. And so when I solved this, I got an x of 4.32 times 10 to the minus 4. And a pH that was minus the log of that, which was 3.36. Did that feel any better? Just throw down a Ka expression. I think starting here is not a bad choice, where we just know, generally speaking, for a weak acid, we can write that Ka is equal to the concentration of hydronium squared over the initial concentration of the acid. And you can find mark schemes where they start with that equation in some form. So it's perfectly acceptable not to show the rice table. What if we had a base? So instead of putting in the acid, what I've done is I've added sodium ethanoate. We still know that the pKa of ethanoic acid is 4.76, but that's not going to describe this solution because this solution has the conjugate base ethanoate. Now, I cross sodium out because it's a spectator ion. All of the alkali metals are spectator ions. They will not affect the pH. So if you put Na plus in solution, it will not change the pH. That's because it's kind of a conjugate to sodium hydroxide, which we'll get to in a second. So what I have in mind here is trying to figure out what we know. What we know is that if we put this weak base into solution, it has to do what bases do, which is take a proton. And make hydroxide. So the pH is going to be greater than 7 because I'm putting a basic salt into solution. And so this hydroxide right there is going to be what's doing it. But I don't know much about this equation, but I do know some other things. So I think that's going to save us. I still know the Ka for ethanoic acid. Acids, of course, donate protons to make hydronium. If I add these two equations together and cancel out anything that appears on both sides, the way I would if I was in algebra, I'm going to get H2O plus H2O makes hydronium and hydroxide. That's crazy because I know everything about that reaction. I know that's the autoionization of water, and I know that its equilibrium constant is 1 times 10 to the minus 14th. When I sum equations, I multiply their Ks. So I'm going to call this first reaction Kb. What happens if I put a base, a conjugate base in this sense, into water, and I'm going to have arrived at the relationship that Ka times Kb is equal to Kw. This one's not in your data booklet, but it is super handy. It tells me things like the stronger the acid, the weaker its conjugate base. It also tells me that if someone were to give me the pKa, I could figure out the pKb by using the same trick we used for the pH. So maybe to solve this particular equation, what I could do is say, you gave me the pKa, that was kind of you, but what I really wish you gave me was something about the base hydrolysis constant, and that value is 9.24. I think we could solve this problem now, but I want to take a short break and just look at this relationship between how strong an acid and its conjugate base are. If we think about the acid reaction, so that's the blue one in the center that I'm boxing. If ethanoic acid is a super strong acid, what that means is that this equilibrium is going to lay really, really far to the right, because every time I put ethanoic acid into solution, it donates a proton. At the same time, what that must mean is that its conjugate base is really ineffective at taking a proton. So you can think about this a little bit in terms of like a Le Chatelier or an equilibrium. If we know that an acid is particularly good at going to the right, that means the base is particularly not good at going to the left. So again, here are some questions to make sure you see that relationship between the acid and the base. And I think they're going to take longer to read than to solve, perhaps. Okay. So how do we know if we have an alkaline solution when something dissolves in water? When we're looking at those salts, what are we looking for? One way to approach this might be to think about the parents that made that salt. And so I wrote down on the last page, like it was obvious that this was basic because I saw the ethanoate ion. And so I just wanted to make sure that we all had a chance to think about that. Um, when I see KBr, what I imagine is KOH and HBr coming together to make water and KBr. And so the parents of this are a strong base and a strong acid, and so it's neutral. When I see NHBr, I think ammonia reacted with HBr. And this time I have a weak base and a strong acid. And so I believe that their product is going to be weakly acidic. And here I have methanoic acid and potassium hydroxide coming together to make potassium methanoate. So that would be a weak acid and a strong base. And so that would be basic. And finally, I have methanoic acid coming together with ammonia. And these are both weak, a weak acid and a weak base. And without more details, I would just tell you that I think it's trending toward neutral. So this question said which one is alkaline or basic, and so the answer is C. And then the next thing, which combination is correct for a very weak base? If you have a very weak base, that means that the Kb is going to be small. It's not very efficient at taking the proton. And so that means its conjugate acid is going to be pretty strong. Let me not say strong. I'm going to say is large. Now, if the Ka is a big number, like 10 to the minus 2, the pKa would be 2. If the Ka were a small number, like 10 to the minus 5, the pKa would be 5. So when I answer this question, I'm looking for a pKa that is relatively low, representing a big value for Ka, and a Kb that is low. So I think the answer is A. Again, with a weak base, I think Kb is a small number, maybe like 10 to the minus 12. I think that means the Ka is going to be a big number, like 10 to the minus 2. Their product is governed by Kw, so their product has to be 10 to the minus 14. The pKa is going to be minus the log of that. So I think A is correct. So let's finish this problem. We just worked on figuring out the Kb for this, and now this problem should look a whole lot like our weak acid problem. I'm going to write down that the base reacts with water to make its conjugate acid and hydroxide. Initially, the concentration is 0.2. The change is that some of this base is going to steal a proton from water to become the conjugate acid and hydroxide, so that at equilibrium, I have slightly less of the base and some of the conjugate acid and hydroxide. So Kb, which is 10 to the minus 9.24, is going to be equal to the concentration of conjugate acid times hydroxide over base, or in terms of x, x times x over 0.2 minus x. Of course, I'm going to call this x in the denominator negligible, and I'm going to try to solve for x. And I get 1.07 times 10 to the minus 5 when I solve for x. Now, x is the concentration of hydroxide. So if I take minus the log of x, I have minus the log of the concentration of hydroxide. That's the POH. And I get a number really close to 5. I asked you for the pH. The pH is 9.04. Feel great about this because I know that the solution has to be basic because I put a basic salt in. The pH is greater than 7. Medina agrees with me, so we're living the dream. Okay. Now, Emma asked, what happens if we have more than one reactant? And so I assume that's where we're headed. What I was thinking about doing is mixing together the ethanoic acid and the ethanoate and seeing how we might approach that. Here is a weak base problem for you to try. The Kb and the initial concentration are given. And so you can decide how many steps you want to use to try to figure out the pH of that solution. Again, this is a real IB question. I don't know why I didn't put the marks on there. I guess it's a 2 marker. I should say a real IB style question. I got another request for the notes. So I might consider just jumping in and saying that KB is 10 to the minus 3.35. It's going to be equal to the concentration of hydroxide squared over 0.240. That would allow me to solve for the concentration of hydroxide. So I did not write down the rice table. If you look in the notes, you'll of course see it there. Just trying to move up a little bit. I got 0.0104 moles per decimeter cubed for this. And so I found the POH to be minus the log of that. And the pH to be 14 minus that. So again, I feel pretty good that the pH is greater than 7, so I don't think I made a silly mistake. I make those often. This is a pretty good weak base. The pKb is a relatively small number. So this seems like it's a pretty good answer. You may ask the question, how did I know this was a weak base? Again, I was given the KB, so that was a big clue it was a weak base. The weak bases that we mostly see are amines. The strong bases that we see are sodium hydroxide, potassium hydroxide, but it's really any group 1 hydroxide, and all of the soluble group 2 hydroxides. So I think those are the ones calcium and below in group 2. For my purposes, I'm pretty happy with sodium potassium hydroxide. Okay, I hope that felt fine. So we can do a strong acid calculation. We can do a strong base calculation. We understand the relationships between H plus and OH minus. And so as I promised, Emma wanted to know what happens if we have more than one reactant. And so here I have both the ethanoic acid that we worked with, it's the same solution, and the conjugate base salt, so sodium ethanoate that we worked with. What is the pH here? And many of you know that this is going to be a buffer system, but let me try to show that to you. To show that to you, what I need to do is I need to figure out what we've got here. And to figure out what we've got, I'd like to know what the concentrations of both of those things are in the mixed solution. And so that's going to take me a little bit. I need to know how many moles of ethanoic acid there are. And so I'm going to take the concentration times the volume. Seems right. And I need to know how many moles of this other thing I have. And so I need to take the concentration times the volume. How many of you know the answer now as to what the pH of the solution is? Right? Couple. So some of you have recognized that the concentrations of the acid and its conjugate base are equal to each other. Cool. Let's move on to the next thing and think about what is the chemical equation that we're describing. The chemical equation that we're describing, since we're given the Ka, is going to be ethanoic acid reacting with water to make conjugate base and hydronium. The way we've set up this solution, we've actually added a little bit of reactant and a little bit of product. Now, when I make a rice table, I always have to do it in concentration units because the equilibrium constant expression is in concentration units, right? It's the concentration of the products over the concentration of the reactants. I just figured out the moles with you, If I wanted instead to know what the concentrations are, I would see that I have to add the 25 cubic centimeters and the 50 cubic centimeters to find that the total volume is 75 cubic centimeters. In other words, the concentration initially of the acid is going to be 0.01 moles divided by 0.075 dm cubed. I still don't care about water because it's still a liquid, so it doesn't appear in my equilibrium constant expression. But I do care about the conjugate base. Its concentration is also 0.01 divided by 0.075. I'm afraid I'm going to get the zeros wrong if I try to pretend I can do that in my head. So I'm just going to let my calculator do this, and I'm going to write this down as a decimal number. So initially, those are the concentrations of the things in our solution. Now the change, this reaction coming to equilibrium, is going to be that the acid is again going to hydrolyze. Now the reason that I believe that the acid is going to hydrolyze instead of trying to come up with something about the base is because the pKa is a relatively small number. The pKa is 4.76. That means that the pKb is 9.24. That means that the acid is stronger than the base. So when these two things are in solution together, my expectation is that the acid is going to be the winner. It's going to be the one that's able to give off protons and make more base. So I believe that I am going to take away some of the acid, and I'm going to make some conjugate base and some hydronium. So that at equilibrium, I have 0.133 minus X, 0.133 plus X, and X. One more time, I'm just going to try to solve this using the K expression. So I'm going to say K is equal to the concentration of the conjugate base times hydronium over the acid. And if I plug in my numbers, I'm going to get 0.133 plus X times X over 0.133 minus X. And I'm going to stay true to myself, and I'm going to say that X is small compared to the initial concentrations. I have a weak acid and a weak base, and the base is actually going to make it harder for the acid to hydrolyze. So X is going to be even more small number. So I'm going to assume that X is small compared to 0.133. And when I do that, I assume it both in the numerator and the denominator. So with X being negligible, K simplifies to 0.133 times X over 0.133, or X is going to be equal to 10 to the minus 4.76. Well, this is looking good. The pH is minus the log of X. And so the pH appears to be 4.76. Now, some of you knew that when we started. Some of you saw that when the concentration of the acid was equal to the concentration of its conjugate base, you knew that the pH was equal to the pKa. You knew that we were at the point that we call half equivalence. And so you're able to read the problem statement, notice that the moles were equal to each other. So they gave me the pKa, the pH is that value. So all of this calculation was kind of extra. When we are at half equivalence, we know that the pH is equal to the pKa. Henderson and Hasselbalch decided to write an equation to make this maybe a little bit easier for us. They said that we know that the pKa is equal to the pH minus the log of the ratio of the conjugate base to the acid. In our problem, these two concentrations were equal because the moles were equal. So we took the log of 1, which is 0. And so at the half equivalence point, the pKa is equal to the pH. If you read through the exam papers from 2016 to last year, what you'll find is this is the only place they asked us about the pH of buffers. In paper 2, we were limited to half equivalence. You just had to show enough working to show that you were at half equivalence. In the new syllabus, it seems that they expect us to do buffer calculations when we're not at half equivalence. That is, it seems that we are supposed to know how to use the Henderson-Hasselbalch equation. It is not given to us in the data booklet, so it is one that's worth trying to learn. I think I wanted to take a minute to identify when you were in the buffer zone. And so when you're in the buffer zone, that means that the concentration of the acid and its conjugate base are approximately equal. So I gave you 4 scenarios there to try to identify when can you use Henderson-Hasselbalch. It's only in the buffer zone. And so I need you to be able to identify when you're in that buffer zone. So I'm going to answer 2 questions while you think about that. Okay, I blew through a few questions. I hope you had a chance to read this. I'm looking for the point when I have about equal amounts of the acid and its conjugate base. So I am neutralizing this weak acid by adding the strong base potassium hydroxide. So I'm going to draw that with a yield 0. Neutralization reactions are always going to completion. And we're going to make the conjugate base and some potassium ions and some water. And what I need to do is figure out the time when the amount of the acid is about equal to the amount of its conjugate base. And so if I had 1 part this, I would love to add 1/2 of a part of this and think about it in terms of a limiting reactant question. So if potassium hydroxide were my limiting reactant and I added about half as much, I would run out of potassium hydroxide. I would be left with half of my original acid and I would make half of the base. So this is what I'm looking for in those answer choices. I'm looking for something where I've added half as much strong base as I had initial acid. And so I need to think about these things in terms of amount or moles. And because one is in cubic centimeters and the other is in cubic decimeters, I thought maybe if I multiplied them together without my calculator, I could think about it in terms of millimoles or no units. So I'm just going to take the 0.4 times the 50 and get 20. And the official unit there is millimoles. But I'm just trying to do this on my test paper that no one's ever going to see, so I probably wouldn't write a unit down. So I'm taking 0.4, I'm multiplying by 100, and in choice A, I'm adding twice as much base as acid. That means all of my acid would be neutralized. 100% of my acid would be turned in to the conjugate base ethanoate, so that's not the right answer. In the second one, when I multiply the concentration times the volume to get the number of moles, or millimoles in this case, I get 40 millimoles of ethanoic acid and 40 millimoles of potassium hydroxide. So one more time, all of my acid would be converted into base. That would be like the equivalence point of this titration. That's not what we're going for. In choice 3, I get 20 millimoles of the acid, I get 20 millimoles of the base. Again, that's like the equivalence point of some titration that I'm not trying to do. So let us hope that D is the right answer. I have 40 millimoles of the ethanoic acid. I have 20 millimoles of the KOH. That is a perfect 1 to 1/2 or 2 to 1 ratio. D is our right answer. So way to go, those of you who wrote in D. Aida asked if we should memorize the Henderson-Hasselbalch equation or just do the Rice thing. I am really terrible at memorizing the equation. I actually just figured it out this morning, so I would be good at writing it down for you guys today. If you're good at memorizing things, it's 100% the first formula that I would worry about memorizing. You can also just try to figure it out with the Rice table. And if you know you have your Rice table as a backup, then you're all set. If you're like, shoot, I don't remember it, do the Rice thing. But if you do remember it, just write it down and think about how much you saved yourself your 90 seconds or whatever. So it's not going to be a huge expensive time to do the writing. But it is nice sometimes when you can skip a step and know that you're going to be able to spend that on something that you need to work out a little bit more. So here's my first like doozy question. And that is, I'm going to take the buffer that we just made. That is the solution that had equal amounts of the acid and its conjugate base. And I was going to throw in 0.4 grams of sodium hydroxide. And so if you're super astute, you're going to know that we started this whole experience by looking at the pH of water. And you told me it was 7 and wondered if you're in the right place. And then we added 0.4 grams of sodium hydroxide to 75 milliliters of that water, and I asked you what the pH was. And then in the last problem, you got the pH of the buffer, and it was 4.76. And now you're going to throw in 0.4 grams of NaOH to 75 cubic centimeters of that buffer and figure out what the pH is. And so I'm trying to prove to you that it buffers. That's my motivation in choosing these kind of weird numbers for the problem. But I want you to feel like buffers work. So I think this problem is fair. But my motivation for choosing these numbers is because I'm trying to tell you this story of the buffer actually doing some buffering work. Okay. You've already done a fair bit of the math for this problem. We were at half equivalence. That is, those two numbers of moles were equal to each other. And I saved them on this page. But we're going to do something terrible and add some more base in. What the base is going to do is react completely with some of the acid to make base of the conjugate variety and Na plus and water. So this goes to completion. This is not a Rice table. And we have the moles. We worked them all out already. We have 0.001 moles of NaOH. We have 0.01 moles of the acid, and we have 0.01 moles of this base. If this reaction went to completion, we're going to use up all of that base. We're going to use up 0.001 moles of the acid and be left with 0.009 moles of the acid. And we're going to make 0.001 more moles of the base. So I did this calculation in moles, not in concentration. And that's because this is a straight limiting reactant problem. This is back to R 2.1. We just have the moles of reactants. We're figuring out how many products they're going to make. It's a straight yield zero. Many of you are excited now because we can move to the next step, which is find the pH. So here's another opportunity to try Henderson-Hasselbalch. It says that the pKa is equal to the pH minus the log of the concentration of the base over the acid. I'd really like to isolate the pH here, but I can't memorize it that way. As I mentioned, I'm really pretty terrible at memorizing this one. So the pH is going to be equal to the pKa, which is still 4.76, plus the log of the concentration of the base, of the conjugate base. So that would be 0.011 moles divided by 0.075 decimeters cubed over the concentration of the acid. That would be 0.009 moles divided by 0.075 decimeters cubed. So the 75 decimeters cubed comes because we added 50 and 25 together when we mix the solution together. So the total volume is 75. Henderson-Hasselbalch requires me to be in concentration units, so I divided the moles by the volume to be there. I plugged this glory into my calculator, and I got 4.85. What an amazing answer. Originally, the pH of this solution was 4.76. When we added base, it became more basic. Sounds like I didn't make a silly mistake, but it didn't change very much. Huh. When I added this same amount of sodium hydroxide to water, the pH actually went from 7 to 12.12. When I added it to the buffer, it didn't change hardly at all. That's what buffers are. They are solutions that are resistant to the change in pH upon the addition of small amounts of acid or base. So I tried to show that to you numerically. When we threw a little bit of base into the buffer, the pH changed by not even 0.1 units. When we threw that same amount of base into pure water, the pH changed by 5 units. So buffers resist change in pH. And how did it resist that change in pH? Well, look what it did. It soaked up a strong base and turned it into a weak base, something that was much less efficient at changing the pH of our solution. So how do buffers work? They take in small amounts of a strong acid or a strong base and convert them into weak acids and weak bases that don't change the pH nearly as much. So the efficiency of a buffer is going to be related to its concentration. If I have a equal amount of ethanoic acid and sodium ethanoate, the pH of my solution will be 4.76. If that equal amount is like 100 molar, you can't get that into solution, but just go with me, then I can add a fair bit of sodium hydroxide before I start changing the solution's pH very much. If those two concentrations are really small, 0.001 molar, if I add a little bit of sodium hydroxide, I'm not going to have the ability to buffer it very much. I'm not going to have the ability to convert very much of it into the conjugate base. So we refer to the concentration of the acid and the base as something along the lines of a buffer capacity or its ability to buffer. So the new assessment statement says you're supposed to know something about the effect of concentration on buffering, and there are no questions about it. So I'm trying to spend a second conveying to you that the higher the concentrations, that is both the concentrations of the base and the acid, as long as they're in that same ratio, the better the buffer will be, the more able it will be to take a strong base and convert it into a weak base, because there will be more material to convert. All right, I hope that worked out okay. Those are the values. I don't think there's anything to add here, just to say that we made a really great buffer. So buffers resist change in pH. upon the addition of small amounts of acid or base. And we can make buffers in two ways. We can make a buffer by taking 1 part acid and 1/2 part strong base, or we can make the buffer by taking 1 part acid and 1 part conjugate base salt. So you had a multiple choice question that helped you with one of those ideas, and we performed the other one where we had equal amounts of the weak acid and the weak base. So those are two ways to make that buffer solution. A buffer has approximately equal amounts of those two things, the acid and its conjugate base. Hope you feel okay with buffers. Frequently, they'll ask you, using equations, describe how buffers work. These are the equations you're going to write down. If you add a base into a buffer, it is going to be converted into the conjugate base. If you add an acid into the buffer, it's going to be converted into the conjugate acid. So you should commit these two equations to memory. Because this is neutralization, because I'm putting a strong acid or a strong base in there, these are yields arrows, not equilibrium arrows. I chose an acidic buffer because most of the questions are about that. You can also choose a basic buffer. It works the same way. I'm going to have approximately equal amounts of a base and its conjugate acid. Same thing happens if I add a little bit of acid in there, we will make some conjugate acid. If I add a little bit of base in there, we'll make some conjugate base. This is the alternate version of the Henderson-Hasselbalch, all in terms of base things. So instead of having the pH is equal to the pKa plus the log of the concentration of the base over the acid, which again, I've practiced all morning, so I can write down, okay, we have the base version of it. I would not memorize that. I just wanted you to know that if you find yourself in a situation where these two things are equal, then you're going to know this equality if it helps you. I would not spend a lot of time. I just want to say the term basic buffer means that the weak base is stronger than its conjugate acid, as in this case. And all of the same things hold true. You can make a rice table if you want. So here are two questions for you. Methanamine is going to be CH3NH2. It's a really common looking organic base, a weak base. So can you show me how that works as a buffer? And then a question that was in the option papers using Henderson-Hasselbalch, a couple of you asked, how else can this come up on a test? So question 13 shows how they asked a question about buffers that's not super numerical. It's just kind of numerical. So I'm going to give you a second to do that. Answer a few in the chat. Okay. So if you took a weak base and you added a strong acid, I'll do HI because that's the one I forgot. I'm going to use a yields arrow and I'm going to show it making the conjugate acid, the methyl ammonium ion, as well as some iodide just floating around doing nothing. And so that's my equation. That's my first mark. My second mark is going to be saying something about how the strong acid is converted into a weak acid. So again, 2 marks, the first one for writing the equation and the second one for saying that a strong acid like HI is converted into a weak acid. You would really like this to say base. You can tell that I was driving off of a question. I didn't alter it completely. I apologize. Calculate the ratio in which 0.1 molar potassium hydrogen phosphate and 0.1 molar dipotassium hydrogen phosphate should be mixed to obtain a buffer with a pH of 6.5 given the pKa. So this was in an option B question on paper 3 in the past couple of years. That's where buffer calculations have been most recently. This equation is going to rely on me being able to write down Henderson-Hasselbalch. Here, the base is the 2 minus, and the acid is the 1 minus. So we're looking to calculate this ratio. And we want to know how these two solutions should be mixed to obtain a buffer with a pH of 6.5, given the pKa of this. So let me remind you that the reaction that we have information about is this one. So that's what the Ka is describing. And we know that if we had equal amounts of these two things, the pH would be 7.2. We would like the pH to be lower than that. So our expectation is that we should have more of this reactant, a more acidic solution. And so this ratio should probably be less than 1. Now, I see that the two concentrations are equal. But when I mix them together, I'm not really interested in what their concentrations were before I mixed them. I'm interested in what their concentrations are in my reaction. And so I need to know how many moles of each of those things I would have. And so the number of moles of H2PO4 would be equal to the concentration times the volume. And so it's really the volume that I'm going to care about when I'm making these solutions. So I'm going to go into the stockroom, I'm going to grab 2.1 molar solutions, and I'm going to ask myself the question, how much of this one and how much of that one, or what volumes of those two things do I want? And so when I'm looking at the ratio in my Henderson-Hasselbalch, what I'm imagining is that I have here the number of moles of HPO42 minus over the total volume of the mixture. That is how much of both of those solutions I bring together. And here I'm going to have the number of moles of the monobasic divided by the total volume. And I hope that you can think through this for a second and see that the total volume is the same in the numerator and the denominator. I hope you can also see that the numerator and the denominator are going to be equal to the concentration times the volume of that solution that I use. Since the concentrations of both solutions are equal, when I take this ratio, those also will cancel. And so this ratio is actually going to be the ratio of the volume of the monobasic to the dibasic. So I hope that feels okay. I think we're answering the question. We just got to plug in some values now. So the pKa is 7.2. The pH is 6.5. And I'm going to rearrange this to say that the log of this ratio which is really a ratio of the volumes of those two solutions I have to use. Maybe some of you did this for your IA. Congratulations on getting those done. Is going to be equal to the pH, which was again 6.50, minus the pKa, 7.20. To get rid of this log, I'm going to do the inverse log on both sides. So those will cancel out, and this ratio would be equal to 10 raised to the power of 0.70. Paper 3 questions have traditionally been super difficult, and I feel like this one doesn't disappoint. It's not an easy problem, but I think it's kind of doable. I got 0.20 when I did it earlier. So I'm telling you, you need 1 part of the basic solution to 5 parts of the acidic solution. And that's what we said before, that we needed more of that acidic solution because we needed the pH to be lower than 7.2. So that seems consistent with my understanding. So I think it's a good answer. So I'm going to move on from it. So I think the top question about how buffers work has been extremely popular on exams. Write down the equation and say a sentence. The second question, again, has only appeared in the options, and I think all of us are guessing as to how much that's going to move into paper 2. It's certainly in the syllabus now, but all bets are off on your tests. So I hope that felt okay. We've actually done all of the hard work to understand titrations. And so this titration is a strong acid with a strong base. So you can see initially, before I've added any sodium hydroxide to my solution, I have a pH of about 1. And since I know it's HCl, its concentration is 0.1. That seems really consistent. I know that the concentration of hydronium ions is meant to be 0.1. So this all checks out. So that point right there is when I have only the acid in solution. I really understand what it is. So the y-intercept is the pH of the pure acid solution. Another point where I really understand what's going on in this curve is going to be halfway between sort of the points where this looks super straight. And unsurprisingly for this calculation, I'm getting something real close to 7. When we mix together a strong acid and a strong base, we make a neutral salt, in this case NaCl, and its pH is 7. It does not change the pH of pure water. It has no acid-base character. This point is known as the equivalence point. That is the point when the concentration of the acid is, ooh, I don't like that. That is the point when the number of moles of the acid is equal to the number of moles of the base. And finally, this point over here, you can see is trending toward 13. It's never actually going to get there because we added the HCl in, so the sodium hydroxide will always be kind of impure. It will always have some extra water in it. Its concentration will never be quite 0.1, but as you add more and more of the sodium hydroxide, you should be asymptotically getting toward a pH of 13. That's because the pOH of the solution is 1, so the pH is 13. So those are the 3 points I want you to look at on this curve. The initial, that's when we only have the acid. The equivalence point, that's when we have completely neutralized the acid. And as it asymptotically approaches whatever it is we're titrating with. The equivalence point, again, is when the moles of acid are equal to the moles of base. The endpoint is a little bit different. The endpoint when you're titrating is when you see a color change. So that's when you stop a titration. You try to set it up such that the color change occurs where the equivalence point is. So you would choose an indicator that changed color really anywhere between 4 and 10 for this, but ideally pretty close to 7. So that is a strong acid, strong base titration. But we've been working with more of the HL content today, and that's when we have weak acids and bases instead of strong. And so on the left-hand side, I have a weak acid with a strong base, and on the right-hand side, I have a weak base with a strong acid. I would like to know what the concentration of the weak acid is. And I would like to know what's in solution at points A and B on each graph. So the deduce the major species at A and B is a riff on an IB question, and the other one is just a check to see how we would do that. I'm going to answer a couple questions in the chat while you think about what's present at points A and B. All right. Thank you for being patient. So the points that we're always going to be checking out, there are 4, but I only asked you about 2. When we increase this wrinkle of having a weak acid or base, you notice the shape of the curve changes. When we had the strong acid, this started down here at 1, and it came up monotonically increasing with no change in concavity, just like a sweet little logistic function, maybe, something like that. But when we have this weak acid, you notice that there is a change in concavity right about here. That is the half equivalence point, and that's the point I tried to show you with A. So you should expect to be able to draw that little like loop-de-loop where it does change from being down to up. And at that half equivalence point, I hope you said that you expected the concentration that mattered to be that of the weak acid and its conjugate base being more or less equal. So at point A, what we have in solution is approximately equal amounts of the weak acid and its conjugate base. At the half equivalence point, that is 25 cubic centimeters, they should be exactly equal. How did I figure out that was half equivalence? Well, I found the equivalence point right here. And that equivalence point of 50 actually allowed me to figure out what the concentration of the ethanoic acid was and find the half equivalence point. Reading off the graph where the equivalence point is, I can see that the volumes of the ethanoic acid and the sodium hydroxide are equal. So their concentrations must be equal because the number of moles has to be equal. That was a lot of words to say. I think the concentration of ethanoic acid in this picture is 0.1. Now, some of you work super hard and you practice so much that you know that you can figure that value out a lot of ways. You could try to read off the pH right here and determine the concentration using the formulas we had earlier. That's working way too hard. When you're asked about the concentration of an acid using a titration curve, I recommend 100% that you always go to the equivalence point and set up a number of moles of acid is equal to the number of moles of base problem. Multiply the concentration times the volume of the base. You know the volume of the acid, so you can deduce the concentration of the acid is 0.1. At point B, at that equivalence point, you have taken the acid, you have added sodium hydroxide, and you have converted it 100% into its conjugate base, water, and sodium ions. What's present at B is just the conjugate base. Over here at A, when we're titrating a weak base with a strong acid, again, we're going to have NH3 in a concentration that should be very much equal to its conjugate acid. And then we are doing the titration where we neutralize the base with a strong acid at the equivalence point when the moles are equal. All of the NH3 should have been converted into NH4+, so the only thing you should have present here is the weak acid. There you go. 2-mark question. What is present? When they ask you questions, there are sort of 2 ways they've done it. So I have a 4-mark question at the top that I think is pretty challenging, and I have 6 marks worth of question underneath that I also think are pretty challenging. But this is the proof that we know everything there is to know about the titration of, in this case, a weak acid with a strong base. So we're going to take ammonium nitrate. So that's just like taking ammonium ion. So I recognize it as an acid, and we are going to titrate it with potassium hydroxide or sodium hydroxide, depending on where you look. My graph says the wrong thing. And we're going to try to figure out what that curve looks like. So in all of these problems, I have the same system. I have 30 cubic centimeters of 0.3 molar ammonium nitrate, and I'm titrating it with 0.3 molar sodium hydroxide. I'd like to know the pH at the beginning. I'd like to know the pH at the half equivalence point. I'd like to know the pH at the equivalence point, and I'd like to sketch the graph. And if I can do those things, this is not going to be 10 marks on any one test, but I think that I can answer any question that they ask me. This is our second to last thing for this morning, so I hope we can do it efficiently. Maybe it would be prudent to do these out of order and to start with what is the pH of that acid solution when it's all we have. So you see this 3-mark question that's 16A. You, unfortunately, were given the pKb of its conjugate base ammonia. Step number 1 is going to be converting from pKb back to pKa and find out for this weak acid ammonium, the pKa is 9.25, or the Ka is 10 to the minus 9.25. Now you know the initial concentration and you know the K value. Are you able to deduce the pH of that system? We practiced this at the beginning. We said that the Ka was equal to the concentration of hydronium ion, which we called X squared, over the initial concentration. And so we could solve that for the concentration of hydronium ion. And take minus the log of that value to get the pH. I got 1.3 times 10 to the minus 5. And a pH of 4.89. So I'm going to mark that on my graph. From 4 to 6, I have 1, 2, 3, 4, 5 units. So I think they're worth 0.4 each. So this would be 4.4, 4.8, just a little bit above it, 4.9. Now, the next point that I wanted to put on my graph is thankfully not an awful one. The equivalence point should occur when the moles of ammonium nitrate are equal to the moles of the hydroxide. I know that I started with 30 cubic centimeters of 0.3 molar ammonium, and I'm adding in 0.3 molar potassium hydroxide. And so the equivalence point should occur at 30. The half equivalence point is going to be at half of 30, which is 15. And at the half equivalence point, the pH is equal to the pKa. So at 15, I should be able to put in 8.4, 8.8, 9.25, a point right there. The last point that I think I should be able to put in is going to be that at really, really large volumes of the base added, the pOH should approach minus the log of 0.3. It's about 13.5. Oh, sorry, that's about 0.5. So I think really long times I should be up here above 13, asymptotically getting there. For question number 16, which is a real question, I don't have to know exactly where this equivalence point is. I can see that it's got to be, somewhere in this general region. And so I could put a little sketch in. And we have done 6 marks of a question. This is a sketch of what the shape of the pH curve of ammonium nitrate would look like when titrated with potassium hydroxide. For question number 15, I'd like to figure out exactly where that equivalence point is. And that's a little bit more onerous. That's why it's worth 4 marks. To do that, I've got to recognize that at the equivalence point, I will have converted all of the ammonium into ammonia. And so let's figure out how many moles of ammonium I have. I have 30 cubic centimeters of 0.3 molar. And so that looks like I have 0.009 moles of ammonia. But at the equivalence point, the total volume is going to be the 30 cubic centimeters of ammonium nitrate that I started with, plus the 30 cubic centimeters of base that I've added, so 60 cubic centimeters overall. The concentration of ammonia is going to be equal to 0.009 moles divided by my 60 centimeters cubed. It's going to be 0.15 moles per decimeter cubed. So this is the concentration of my base. The Kb is equal to 10 to the minus 4.75. And so I can set up the same equation that we've been using all morning or night, where the concentration of hydroxide times the concentration of conjugate acid over the concentration of the base is equal to the Kb. I assume that X is small. I then solve to figure out that the concentration of hydroxide is equal to 0.00163, or the pOH is 2.79, and the pH is 11.21 gross. So this point where we just estimated it in question number 16, we found precisely should be at 11.2. So I drew it a little bit high in my estimate. So this question I think is kind of hard and really mathy. This question I think is pretty reasonable. It's a sketch and it seems to be more in keeping with how I think the new curriculum is going. So I got a few questions about this. Some of them are in the Q&A, so let me try. The first one is, why is the half equivalence greater than 7? At the half equivalence point, I have ammonia and ammonium in equal amounts. And ammonia is a stronger base than ammonium is an acid. So the pH is greater than 7. And I also got a y is H3O plus squared. And that's because it's the concentration of hydronium times the concentration of conjugate base in the numerator. And those values are equal. So we write x squared. Hope that helps a little bit. Aida said that graphing these is still confusing. What are some good ways to self-study this? I think that's a fantastic question. The RV webpage does have a few examples, but I think also if you can just find a curve like this and think about what you know. So if I just look at the curve on the right, I can see where the equivalence point is. And so I could figure out the concentration if I made something up. So maybe I'm going to tell you that the HCl is 0.2 molar. And maybe I'm going to know that I had 25 cubic centimeters of my weak base. And I'm going to ask on my own time, what must the concentration of my weak base be based on this picture? And then I'm going to look at the half equivalence point. I'm going to ask myself, what is the Ka of that weak base? I'm going to look over here and say, could I see how well I did? Does it make sense that I'm getting a pH here? Because now that I know the Ka and I know the concentration, I should be able to determine the pH. So I think that if you just find any honestly graphed pH curve, you might be able to practice the skills. And the skills, again, are thinking about 4 points. The initial concentration, which we've done several problems on this morning. I know you can do it. The half equivalence point, where the pH is equal to the pKa. The equivalence point, which is the super tough one. And the asymptotic behavior, when we just take the pH of the strong acid or the strong base and figure out where it's tending to. It won't ever hit there. You just have to sort of go in that direction to show you understand. So we're looking for 4 points and a smooth curve to connect them. But what I do is I just try to find, like, just search weak acid titration curve or go to the website and look at 3.1 and you'll find some there. Okay, thank you for doing that with me. This is the very last thing. I appreciate how patient and thoughtful your questions have been. The last thing is a really special case to me of buffers, and that's indicators. And I didn't come up with a slide because this question had really what I thought you needed to know most in it. And I thought we might all be tired by now. So this is something you should be able to write down. This is how indicators work. Indicators work because the acid and its conjugate base are different colors. And so if they say, using equations, show me how indicators work, it is exactly what's in that red box they want you to write down. And then you can apply Le Chatelier's principle, and you can say to yourself, what happens if I add acid? Well, if I add acid, I'm going to increase the concentration of H+. And so Le Chatelier tells me that if I increase the concentration of a product, a reaction will shift backwards to undo that stress. And so that means that it will appear color A. Similarly, if I add a base, what's going to happen is the base is going to react with the H+ ions. It's going to make water. And when it reacts with those H+ ions are going to go away. And when we lose a product, Le Chatelier tells me that the reaction should shift forward to undo that stress and make more of the product. Consequently, my stuff should appear B. And so I have this nifty little system where if I add acid, it looks A color, and if I add base, it looks B color. Well, I could imagine then when it changes colors. It's going to change colors when the amount of A color is about equal to the amount of B color, or when the concentration of H indicator, the protonated indicator, is equal to the concentration of the deprotonated indicator. Well, we're back to Henderson-Hasselbalch. The pKa is equal to the pH minus the log of the concentration of the indicator conjugate base over the protonated indicator. Boom. When these two things are equal to each other, I'm taking the log of 1, which is 0. The pKa is going to be equal to the pH. Oh, this is crazy. So what you're telling me, if we're having a better conversation perhaps, is that an indicator changes color when the pH of the solution is equal to the pKa of the indicator. If I look at my titration curve, I want my indicator to change color right there. So I want the pH at equivalence to be equal to the pKa of the indicator. So in the solution that I am measuring, I will be at the equivalence point. I will have converted all of the acid into its conjugate base. But in what I'm using to measure it, the indicator, I will be at half equivalence. That's subtle, but really important. This statement, which is perhaps not really well formed, the pH at equivalence is equal to the pK of the indicator, should answer every question along with the boxed equation in red. So let's see what that looks like. Which statement about the dissociation of the indicator is correct? In a strongly basic solution, color B will be observed. If a solution is strongly basic, we will shift this equilibrium to the left and we will see color A. So that's not good. In a strongly acidic solution, oh my goodness, I don't think I did good on that. Let's reread that. Take away my X and admit I'm getting tired. In a strongly basic solution, color B will be observed. So in a strongly basic solution, I will eat all of my H+. So this concentration will go down. The reaction will shift to the right. And I will indeed see color B. I think that's true. Apologies. In a strongly acidic solution, I will increase the amount of product. The reaction will shift to the left. I will see color A. That's no good. Okay, this one's interesting. The protonated indicator concentration is greater than the deprotonated indicator at the equivalence point. Remember, we're doing a titration. When we speak of the equivalence point, we're speaking about the equivalence point of that acid-base titration. At the equivalence point of the acid-base titration, we want the amount of the protonated indicator to be equal to the amount of the deprotonated indicator because we want the color change. We want to see our bromocresol green turn green. We want to see our phenolphthalein turn palest pink. We are looking for that color change to know that we've hit the equivalence point. So we want those two things to be approximately equal. In a weakly acidic solution, so if we just have a bit of H+, we would again assume that we're going to be seeing the protonated indicator. We assume we'd be seeing color A. So I think that A is our best choice. We got there. Second one, we're going to take sodium hydroxide. We're going to combine it with methanoic acid. So we have a weak acid. We have a strong base. That means they're going to come together to make a basic salt. Or at equivalence, the pH is going to be greater than 7. I want to choose an indicator with a pH range that is bigger than 7. And so my best guess here is phenolphthalein with a pH range between 8.2 and 10. Again, I'm trying to match the pK of the indicator. That's what this value is to the pH at the equivalence point, which I was able to deduce was bigger than 7. All right, you did it. Those are the questions that I prepared for you. The end of this is just the different assessment statements and linking questions and stuff like that that I have reworded from the syllabus guide if you want to go through acids and bases and pretend that you're not an expert at it all at this point. I hope you had fun. If you have more questions, I'll stick around for a bit. If not, that's cool too. I'm just making a blank sheet in case you have questions. Best of luck with your exams. Thank you so much for coming today. I hope you have a great rest of your day. So Scarlett asked me to do number 18 again. And I got a question about NMR, so let's see if I can help at all. Okay, so in 18, I think I was going fast because I wanted to hold this to an hour and a half, and I almost managed. We're looking for the best indicator for a titration between a strong base and a weak acid. So I'm just going to delete everything here so maybe we can focus. And so the question is, we have sodium hydroxide, and we're reacting it with methanoic acid. And so we're going to make water and sodium ions and methanoate. And so what I was trying to convey, but maybe not successfully, is that when I see this, I recognize that it's a base. And if you don't recognize it's a base, that's cool. There's another way to see that. We could also remind ourselves that we have a strong base and we're mixing it with a weak acid. We know it's a weak acid because it's not one of the big five. And so we know that the strong thing is going to win. And so our solution at equivalence is going to be basic. So at the equivalence point, I am confident that the pH is going to be greater than 7. So I want an indicator that's going to change colors with a pH greater than 7. And so I looked at the table and I found phenolphthalein where the color change occurs with a pH greater than 7. So I felt confident it was the best answer. If instead we had a solution where we were taking ammonium ions and reacting it with a strong acid. Oh, sorry. There we go. Because I have a weak base and a strong acid, when these two things come together, they're going to make a weakly acidic solution. So the equivalence point would be less than 7. And here I would be able to choose either one of these indicators. So I'm trying to match where the color change of the indicator happens to where the equivalence point of my titration is. So I have to answer 2 parts of that question. I hope that helps, Scarlett. Okay, Ibrahim wanted to go back and look at the buffers. There was a multiple choice question that wasn't so good. Maybe this one? I think it was after this one, so I don't know. Ibrahim, if you want to give me a hint what you'd like, I'm happy to help if you're still here. Aida. Hey, thank you so much for coming. I appreciate it. Yeah. I hope that helps you. All right. I hope you guys all have a great day. It's been super fun. Good luck with exams.